Okay, that's perfect. Cl plus MgCl. Sorry, did you put Cl1?
Mm,
Was that Cl1?
no, it's two.
Sorry?
It's two.
Okay, so what? Okay, two, correct. Awesome. Okay, now let's see. Now, actually, you can try that for other acids, but you should get to understand that dilute triazonitrate 5, which is HNO3, they are most times not used for the preparation of hydrogen. You can use other acids, but dilute triazonitrate are not used because of its strong oxidizing ability, strong oxidizing property. Now, dilute, please note that down, HNO3. Dilute HNO3 are not used for preparation of hydrogen. Why? Because of its strong oxidizing property. Now, the industrial preparation of hydrogen, or let's look at, or before that, let's look at the preparation of dry hydrogen. Preparation of dry hydrogen. Now, which brings us, now the hydrogen gas produced most times, uh, the hydrogen gas produced most times contains, containing that's tetraoxosulfate 6 acid or anhydrous calcium 2 chloride. Please note this, that whenever hydrogen, any substance or any elements we want to produce, or a gas we want to produce, and whenever they are mixed up with concentrated tetraoxosulfate 6 acid, that's H2SO4, or anhydrous calcium 2 chloride, note that these are most drying agents, either H2SO4, conc H2SO4, and anhydrous calcium 2 chloride. These are drying agents. So because when any gas is being passed through any of these two substances, they are used as drying agents. Now, industrial preparation of hydrogen. Hydrogen can be prepared industrially by different methods. Number one is water gas. Water gas, the last time we talked about water gas was when we studied carbon and its compound. We talked about water gas. Now, it can also be prepared from natural gas, which is methane. That's when natural gas is heated to a temperature of 1000 degrees Celsius. When methane is heated to a temperature of 1000 degrees Celsius, hydrogen is produced. Okay, sorry, have you done organic chemistry?
No.
Okay, but did we do organic chemistry the last time we met?
Yes.
Okay, um, when an organic compound is heated to a very high temperature, such as that, that is called cracking. Now, thermal cracking. Now, what is cracking? Cracking is the breaking of large molecules of hydrocarbons into smaller molecules. Now, when it is heated, when CH4, that's methane, is heated, it produces hydrogen and carbon. This is coming. Let me see if I could write that out. Now, this is, oh God. Okay, don't mind this. Now, now we're having So that is cracking. Now the next one is remember that's from natural gas. The hydrogen is produced. The next one is from hydrocarbons. From hydrocarbons. Please write this. When hydrocarbon, either propane or ethane, either propane or methane, is mixed with steam, it is heated to a temperature of 800 degrees Celsius. It is heated to a temperature of 800 degrees Celsius in the presence of nickel catalyst. Now, when an hydrocarbon is heated in the presence of steam to a temperature of 800 degrees Celsius in the presence of nickel catalyst, two things are produced, which is CO, which is carbon oxide or carbon monoxide, and hydrogen. Now, the mixture of these two gases are called synthetic gas. Remember, we did that in carbon and its compound. Why the mixture of CO2 and hydrogen, they are called water gas. I hope you can still remember that.
Yes.
Okay, so CH4 plus H2O, that's H2O is a gas because it's steam, gives you CO plus 3 molecules of hydrogen gas. That's a synthetic gas. Now, when you react this synthetic gas with more steam, what happens is that that's the CO2, it gives you CO2 plus hydrogen, which is the water gas now. When the synthetic gas is reacted with more steam, that means CO plus H2 plus H2O, it gives you CO2 plus H2, which is the water gas. Now, CO2, we need CO2 to be removed from that equation. Therefore, we use a kind of a drying agent. Now, we can't use concentrated H2SO4, or rather, we use an alkali to dry up, that's to remove that CO2 gas. And which alkali can remove that CO2 gas? That is sodium hydroxide. So please note that even when we are going to talk about air, that's if you be treating air, there are some specific compounds that can remove some gases. An example is CO2. Sodium hydroxide removes CO2. Sodium hydroxide removes CO2. Okay. We have other methods of obtaining hydrogen, which is from coal. Okay, you can obtain that from coal. Probably you can also go that on your own, but I'll just give a brief explanation of that. That steam is passed through hot coal to obtain water gas. And remember, if water gas is obtained, remember when we obtained the synthetic gas, what did we do to synthetic gas? We passed it through more steam. And when we passed it through steam, it gave us water gas. But now, steam is passed through red hot coal. When steam is passed, that's H2O plus coal, which is C, it gives you water gas. It gives you, it gives you the synthetic gas. Now, synthetic gas again is passed through more steam to give us our hydrogen and CO2, which is the water gas. And remember again, the same CO2 is passed through alkali, that's sodium hydroxide, to remove it. So it's Industrial preparation of hydrogen from natural gas, from hydrocarbon and from coal is just similar because steam is passed through hot coal and that gives us um, synthetic gas. Now, the same synthetic gas is passed through more steam to obtain a water gas, which is CO2 and H2O. And sorry, CO2 and H2. And then because of that, it is passed through sodium hydroxide to remove CO2. Okay, let's look at the properties of the physical properties of hydrogen. One of the physical properties of hydrogen is a colorless gas, odorless gas, and a tasteless gas. Hydrogen is a colorless gas, odorless gas, and is a tasteless gas. Hydrogen is colorless, odorless, and tasteless. Okay, hydrogen does not support combustion. Hydrogen does not support combustion. Okay, it is 14.4 times less than air. It is 14.4 times less than air. It is neutral to litmus and insoluble. It is neutral to litmus and insoluble in water. It is neutral to litmus and insoluble in water. Okay, but let's look at the chemical properties of hydrogen. Now, we know definitely that hydrogen can donate a single electron to form a positive ion and can also accept electron to give a duplex structure. That means hydrogen can, to form a negative ion. Hydrogen can also share electron with another atom to form covalent molecule. That's so strange. So the chemical properties of hydrogen, we know that hydrogen can actually undergo three things: donate an electron, accept electron, and also share electron. So with this now, this alone, with what we've done, you can actually show when hydrogen accepts electron, that's to form a positive ion. So you should show us when hydrogen, donates electron. When hydrogen donates electron, okay, you should also show us, you can also show us where hydrogen accepts electron, and definitely you can also show us when hydrogen, okay, can you show me any reaction that involves hydrogen giving out electron and accepting electron? Can you think of any reaction?
Mm.
Can you think of any reaction?
Yeah.
You said?
Um, oxidation.
Sorry, I didn't get you. You said what?
Oxidation reaction.
Um, no. Could you show me one? So what's happening to hydrogen here? Sorry?
Mm. Mm.
What's happening to hydrogen here?
Give us a reason.
Sorry?
Give us a reason.
Okay. This is something I want to show here. Now, to lithium. Now, you did well. You did well. Okay. So lithium here, hydrogen is actually adding one. So that becomes lithium. Now, in this case here now, lithium hydride, hydrogen is trying to, in lithium hydride, this is a strong electropositive metal, and hydrogen is trying to accept an electron from lithium. So it's not balanced. We just put 2 and put 2 here. Now, for acting as a covalent compound,
Close the door.
hydrogen plus now with this now we are having hydrogen flow, right? No. So with this now, hydrogen is trying to share an electron. Now, these are covalent hydrides, that's non-metallic hydrides. Okay, definitely hydrogen reacts with sulfur to form hydrogen sulfide. Now this smells like a rotten egg. This smells like a rotten egg. And it reacts now with when you go to the lab and you do a reaction of hydrogen with sulfur, you start perceiving like a suck away. That's a rotten egg smell. That's really, really bad. And hydrogen can also react with nitrogen. When hydrogen and nitrogen comes into play, we form ammonia. Now, these are some of the reactions of hydrogen. These are some of the reactions of hydrogen. Remember, I said hydrogen reacting with sulfur, and it gives you H2S. Now, the same hydrogen reacting with nitrogen. The same hydrogen reacting with nitrogen, then it's giving you NH3. So in balancing it, I think we have 2 here, and then we have 3 here. Okay. All right. Now, another thing, another test of hydrogen is this, that hydrogen bonds in air. Now, in everything, you should be able to understand what we call the test for hydrogen. Now, the test for hydrogen, please write this down. Write this down, very important. Test for hydrogen. Hydrogen bonds in air with pop sound. Hydrogen burns in air with a pop sound and the formation of steam. Hydrogen burns in air with a pop sound and the formation of steam. Now, if hydrogen gas is produced and for you to test for the presence of hydrogen, and probably you bring it, you want to test for the presence of hydrogen. One of the things we do is you hear the sound pop. It's a pop sound. Now, when you hear that sound, that tells you that, oh, that gas that evolved at that moment was actually hydrogen. So remember we said hydrogen does not support combustion. So once maybe a place is actually burning and you place hydrogen gas into it, what happens is you hear that sound, that pop sound. So that tells you that, okay, this was actually hydrogen. Okay, let's look at the uses of hydrogen. What is hydrogen used for? One of the things that hydrogen is used for is used in the synthesis of ammonia. Ammonia is actually used in the manufacture of fertilizers, for drugs, for plastics. So hydrogen is one of the starting material for ammonia. Okay, and that same ammonia is used for fertilizers, drugs, plastics, and others. Number two, another thing about hydrogen is, okay, did you get what I said first?
Yes.
Okay. Another thing about hydrogen is that it's used in the hardening of vegetable and animal oil for the manufacture of margarine. For margarine, for candles, for soap. So hydrogen is used in the hardening of vegetable and animal oil for the manufacture of margarine. One very good use of hydrogen is most times we use hydrogen to inflate airships and balloon. It's used to inflate airship. That's what's this thing again? Airship and balloon. But hydrogen can be flammable. Most times the use of hydrogen in balloon, the use of hydrogen in balloon is due to its low density. Why is hydrogen used in balloon? The use of hydrogen in balloon is because hydrogen has a low density. Remember we said it's 14.4 less dense than air. So because of that, it's used in balloons. Okay. Now, when hydrogen comes in combination with oxygen, that's we call it hydrogen flame. Those small quantities of hydrogen can be used to produce high temperature that can melt metals. Now, gaseous hydrogen can be used, gaseous hydrogen and with liquid hydrogen, they are used as rocket fuel. Liquid hydrogen can be used as rocket fuel. So these are just a few uses of hydrogen that we can use it for. Remember I've told you about the test for hydrogen, that if you put a lighted splint in a gas jar of hydrogen, what you would notice a pop sound. Just get, we produce hydrogen by using, remember in the lab, get zinc, zinc pebble or the zinc pebbles, get a zinc and then your dilute mineral acid H2SO4 or HCl. What will happen? Hydrogen will be produced. How do you know hydrogen is produced? Just take a lighted splint and put it into that gas jar of hydrogen that is produced. You will notice, you will hear that pop sound. So that shows that hydrogen was actually present. I hope you understand that.
Yes.
Maybe you could try that when you resume again. Maybe you could try that. That is very, some of these things are awesome, Okay, let's go quickly to oxygen. We're going to talk about oxygen now. Now, One of the things we know about oxygen, oxygen is the most abundant, one of the most abundant elements on Earth. It's okay. Can you hear me? Can you hear me?
Yes.
Okay.
Yes, sir.
Oxygen actually is strongly electronegative, chemically very reactive. Oxygen most times reacts with metals to form basic oxides and metals to form basic oxide, non-metals to form acetic oxides. Now, we are going to be dealing with oxygen that we know the oxides of oxygen are basic, acidic, amphoteric, and neutral oxide. Now, we also have what we call peroxide. That's peroxide most times is prepared by the action of dilute acid on certain metals. Now, one of the allotrope of oxygen, which is very, very unstable, is the ozone, which is symbolized by O3. Now, the ozone is an allotrope of oxygen. And remember that what's the purpose of the ozone layer? The ozone layer in the Earth's atmosphere acts as a protective shield, preventing us from too much ultra radiation from falling on Earth and harming living organisms. Now, let's come back to oxygen. Sorry, can you remind me what's the group of oxygen? Or what's the atomic number of oxygen? Let's start with that.
8.
Yeah, 8. And what is the group of oxygen? What group does oxygen belong to?
Um,
Sorry? Don't tell me you've forgotten. Phosphorus now. What group does phosphorus belong to?
5.
5. So you're coming up now. Okay. I will still test you again. No way. What group does potassium belong to?
1.
Potassium.
Yes.
Are you sure?
Yes.
Calcium.
2.
Are you looking? Don't tell me you're looking at something there.
No, I'm not at anything.
Oh, I was just surprised. Why would oxygen now take you that long time like that? Okay, no problem. So oxygen belongs to group 6. We know that. Now, let's look at laboratory preparation of oxygen. Laboratory preparation of oxygen. Now, oxygen can be prepared in the lab by the thermal decomposition. Let's see if I could get that down. The thermal decomposition of salts containing ions rich in oxygen. Now, an example of such is KClO3, which is potassium trioxochloride 5. Now, what happens to this is KClO3 is actually heated. Remember, we said thermal decomposition, so heat is involved. When it is being heated in the presence of a catalyst, and the catalyst is manganese 4 oxide. when it's been heated. So what happened? KCl and 3 molecules of oxygen gas is produced. So this is how we know that oxygen has been produced. But definitely it's been illustrated or it's been symbolized by some things. We know oxygen has been given off by some 1 or 2 ways that okay, this is how we just know that oxygen has been released. That's when we come to tests of oxygen. The test of oxygen. Okay, this is it. KClO3, um, MnO2, which is manganese peroxide, which is the catalyst. Heat is being applied to this, to KClO3, to give KCl, to give that's 2 KCl plus 3 molecules of oxygen gas. All right. Another way it can be produced in the lab is by the decomposition of hydrogen peroxide. By the decomposition of hydrogen peroxide. Now, in this case, no heat is applied. Remember, the first one, heat is applied, but this one, no heat is applied. But immediately, manganese peroxide touches hydrogen peroxide, which is H2O2, effervescence occurs, releasing the oxygen gas. Remember, all these are made in the presence of a catalyst, and that catalyst is MnO2. What does the catalyst do? It just speeds up. The catalyst in this case is a positive catalyst. It speeds up the rate of chemical reaction. It speeds it up. So that's the essence of the catalyst there. That's the essence of it. Now, if we want to obtain dry oxygen gas is obtained by passing it through concentrated H2SO4. Remember, I said the essence of H2SO4 there is to dry the gas, is a drying agent. So that's the essence of that. And it is collected by downward delivery. Why is it collected by downward delivery? Because pure oxygen is slightly denser than air. Remember, we said that hydrogen is lighter than air, so that will be collected by upward delivery. But for oxygen, oxygen is slightly denser than air, so because of that, it will be collected by downward delivery. Do you understand that statement I said? Do you understand that?
No.
Sorry?
No.
Okay. Now, this is what I said. Now, when we talk about, I think I need to even show you. Oh, let's see. Now, I said something that hydrogen is, I said something about hydrogen, that hydrogen is lighter than air, right?
Yes.
Hydrogen is lighter than air, and because it is lighter than air, it's very light, it's lighter than air. So it can be collected by the upward delivery because it's lighter than air. Whatever thing that is lighter than air would easily float because it's lighter than air. But oxygen in this case, I said it's that's pure oxygen, is slightly denser than air. And because of that, it is collected by downward delivery. That means we just apply the principle of density to oxygen and it just wait. Have you used the separating funnel before?
Yes.
Okay, when you are trying to separate oil and water, now you can collect your water very easily. Why? Because oil is less dense than water. So what happens is this: you collect your water first, leaving the oil in the separating funnel, isn't it? You just applied the principle of
Yes.
density. Now, that's actually the same thing I said, because it is slightly denser than air, that oxygen, dry oxygen, pure oxygen, can be collected by downward delivery. So that was just what I was trying to explain. Now, industrial preparation of oxygen. Now, let's look at the industrial preparation of oxygen. Now, from liquefied air. Now, please write this down. Oxygen is obtained industrially from atmospheric air by liquefaction. Oxygen is obtained industrially from atmospheric air by liquefaction. Now, the gas, we want to liquefy it, turn it into liquid. Okay, now, by liquefaction, followed by fractional distillation of the liquefied air, followed by fractional distillation of the liquefied air. Now, how do we do that? How is that being done? There are four processes. There are four processes how this can be obtained. Number one, the atmospheric air is purified. Atmospheric air is purified by the removal of carbon dioxide, water vapor, and dust.
So can you put what you said?
Sorry?
Can you put what you said?
Okay. I said the atmospheric air is purified by the removal of carbon dioxide, water vapor, and dust. Now, I want to ask you this question. How is carbon dioxide removed?
I drying sodium hydroxide.
By using what?
Sodium hydroxide.
Sodium hydroxide. Awesome. That's what I wanted to. Now, by the removal of carbon dioxide, water vapor, and dust. Now, the second process, the purified air is compressed at a temperature of 200 atmosphere. Liquefied air is compressed at a temperature of about 200 atmosphere. The purified air is compressed at a temperature of about 200 atmosphere, heated and then cooled. Heated and then cooled. Heated and then cooled. Now, remember, the purified air compressed, it is heated, it becomes a liquid, it is then cooled. Now, this successful heating and cooling the purified air, now by this heating and cooling, the pure air becomes liquefied at minus 200 degrees Celsius. The pure air becomes liquefied at about minus 200 degrees Celsius. Now, this is actually liquefaction. That means heating and cooling remember this is the liquefied air. Now, one thing we know is that air contains carbon dioxide, water vapor, dust, oxygen, and nitrogen. Now, we have finally, now look at this. Now, Now, this is air. For example, let's assume this is air. Air contains CO2, water vapor, oxygen, and then this is nitrogen, please. And then dust particles. Let's use Si, that's silicon oxide. Let's use that for this. Now, the first thing we did to this air was that we passed it through. We removed CO2, water vapor, and dust. Remove this dust. This was gone. Okay, use a different marker. Now, this was gone. This was gone. This was gone. So what is left?
Oxygen and nitrogen.
What is left?
Oxygen and nitrogen.
Sorry?
Oxygen and nitrogen.
Okay, oxygen and nitrogen. So remember, this is what we want. We want oxygen. So how do we remove nitrogen? Because nitrogen contains about 78% of air. So how do we remove nitrogen? Now, please write. The liquefied air is then fractionated by boiling. The liquefied air is then fractionated by boiling. That's the same thing when you do to same thing we do to petroleum, crude oil. By you pass it through a fractionating column. So liquefied air is then fractionated by boiling. Now, this is so amazing that nitrogen is very volatile. Nitrogen boils first. So that removes nitrogen from the equation. Nitrogen boils first at minus 196 degrees Celsius. Remember, it is already minus 200 degrees Celsius. So when it is being boiled, when it is fractionated by boiling, nitrogen becomes the first product that comes out. So nitrogen, being volatile, boils first at minus 196 degrees Celsius. Minus 196 degrees Celsius, leaving oxygen, which is 99.5% pure. Leaving oxygen, which is 99.5% pure. Now, this process or this separating technique is called fractional distillation. We understand fractional distillation before now when it comes to petroleum. Now, this liquefied oxygen is stored in cylinders, most times for medical use. Especially those that have what they call this. Forgotten this. I'm trying to remember these people that have breathing issues. Now that's what they use for. That's what they use in medical. They use for medical uses and industrial uses. So this is how oxygen is made from liquefied air. Remember, carbon dioxide. Remember the first thing. Now we'll just go through them for the last time. The first thing is that okay. I'll just go through that for the first thing is that atmospheric air is purified by the removal of carbon dioxide, water vapor, and dust. The purified air is compressed at a temperature at pressure of about 200 atmosphere, heated and then cooled. This heating and cooling makes the pure air to be liquefied at minus 200 degrees Celsius. The liquefied air is then fractionated by boiling. and nitrogen comes out first, leaving oxygen, which is 99.5% pure. This process is called a fractional distillation, this separating technique. All right. Now, oxygen can also be prepared by electrolysis, but we'll not go into that now. Now, let's look at physical properties of oxygen. Now, oxygen, pure oxygen is a colorless gas, it's odorless, and it is tasteless. It is colorless, it is odorless, and it is tasteless. Now, pure oxygen is also slightly denser than air. It is slightly denser than air. Number two, it is also slightly soluble in water. It is slightly soluble in water. Oxygen also is diatomic gas and it is neutral to litmus paper. It's a diatomic gas. You can't see oxygen existing alone. It is diatomic O2 and it is neutral to litmus. Now we're going to look at the chemical properties of oxygen. Chemical properties of oxygen. And we'll be looking at, some chemical properties of oxygen. Number one, reaction of oxygen with metals. Reaction of oxygen with metals. Now, this group of metals I'm going to mention now, they burn very brightly when they react with oxygen. Now, these metals are sodium, calcium, magnesium, aluminium, zinc. They burn very brightly when they react with oxygen, in oxygen. But these other ones, but these other metals, okay, but these metals such as silver, gold, and platinum, they do not react with oxygen. They are very low in the reactivity series, so they do not react with oxygen. Okay, now an example of a reaction of metals with oxygen is when we use when we use sodium plus oxygen. Now, if we try to react sodium with oxygen, that's a very vigorous reaction. Now we should be having N2O. Okay. Now this is 4. Now this is a very vigorous reaction and it's not advisable you try that. In fact, one of the reactions you must stay away from is sodium and potassium reacting with oxygen. Okay. Okay, sorry, that was with water, not with oxygen. What else, sir? Okay, let's look at reaction. Sorry, what I said before was sodium with water, not with oxygen. That's a very vigorous reaction. Now, reaction with non-metals. Reaction with non-metals. Okay. Now, the non-metals, before we go into non-metals, most oxides of metals are generally basic. So if you react like most of potassium, calcium, when you react them with oxygen, they're actually called basic oxides. Basic oxides are oxides formed when metals react with oxygen. So most of them are basic oxides. But how do we form acidic oxides? Acidic oxides are formed when non-metals react with oxygen. When non-metals react with oxygen, what follows? Acidic oxide. An example of such is carbon with oxygen. When carbon reacts with oxygen, sometimes we have CO2. Now, this is an example of acidic oxide. So they start forming acidic oxides or acidic anhydride. What are acidic? This acidic anhydride is when we have this acid dissolving in water to form acid solutions. So they become acidic anhydride. Okay. Another thing also we should note is the test for oxygen. Remember, the test for hydrogen was that hydrogen gives a pop sound when it comes with when a lighted splint is put into it. What's the test for oxygen? Oxygen is identified by its ability to rekindle a glowing splint. Now, when you bring a glowing splint to oxygen, that's what do I mean a splint? When you strike a when you strike a match, you notice it brings out that fire. When you put it off, there's this red um, flame, just this faintly red flame that if you blow it, it burns brightly, then it goes off again. That's a glowing splint. Now, when oxygen is brought before a glowing splint, what happens? It rekindles it. Now, in fact, this should help us to know that this is a test for oxygen. Have you noticed? I wouldn't know if you've been to the village before, but one of the things they do in the village is when they use a firewood, you discover that they bring all the ashes or the wood that have become splints when the flame is gone. They bring all of them together and they start fanning it. Sometimes they use their air to blow it, or they use something to fan it. When they fan it, what do you think happened?
The, the fire comes back.
Yeah, the fire comes up again. That's just a very clear example that oxygen rekindles a glowing splint. The fire just comes up like that. But see, that's not the ultimate test. Now, this distinguish oxygen from every other element or compound except one. I must tell you this, so you should note that this there's another compound that does the same thing with oxygen, which is nitrogen 1 oxide. So if you bring nitrogen 1 oxide and oxygen together and you bring a glowing splint, funny enough, nitrogen 1 oxide will also rekindle this glowing splint. But how do you distinguish it? How is it being distinguished from oxygen? How do you distinguish it from oxygen? One of the things you use to distinguish that from oxygen is that oxygen is tasteless, is odorless, but nitrogen 1 oxide has a pleasant, sickly smell. Nitrogen 1 oxide has a pleasant, sickly smell. Nitrogen 1 oxide has a pleasant, sickly smell, but oxygen is odorless. This is a very good why question. Like oxygen and a particular compound, they rekindle a glowing splint. What is that compound? You tell them. Now, how do you differentiate oxygen from that same compound? Number one is that oxygen is odorless. Nitrogen 1 oxide has a pleasant sickly smell. That's not the only way. Number two, oxygen reacts with nitrogen 2 oxides to give. Number two is that um, I'm gonna show that to you. I'm gonna show that to you that oxygen reacts with nitrogen 2 oxide to give brown fumes of nitrogen 4 oxide, why nitrogen 1 oxide does not react with it. Oxygen reacts with nitrogen 2 oxide to give brown fumes of nitrogen 4 oxide, but nitrogen 1 oxide would not react. So these are the two basic ways you can distinguish oxygen from nitrogen 1 oxide because their tests are similar. A glowing spirit will separate oxygen from every other compound and element, but except nitrogen 1 oxide. So how do you differentiate it? Number one, from the smell, and number two, using nitrogen 2 oxide. Okay, okay. We've talked about allotrope, that ozone is an allotrope of. Now, what's an allotrope? What's an allotrope? Can you remember that? Oh, you are muted.
When
Sorry? What did you say?
yeah, when the same elements, when when some elements exist in more than one form.
Yes, allotropes are when when we have two or more different forms of the same element. The example is carbon, which is graphite and diamond. Now, oxygen has an allotrope, ozone, and then sulfur also have allotropes. We call them monoclinic, rhombic, and amorphous sulfur, and others. Now, phosphorus also has its own allotrope. Okay, I think we are almost getting to the end of oxygen, so let's see what to do on that. Now, let's look at compounds of oxygen that the oxides of oxygen. Oxides of oxygen. Okay. Now, oxygen, I said it before that oxygen has four oxides. Now, one of the oxides of oxygen we have the acidic oxides. Now, I told you then that acidic oxides, these are non-metals that dissolve in water to form acidic solution. That's acid anhydride, and they react with B's to form salt and water. Examples of these acidic oxides, examples of these acidic oxides, um, examples of these acidic oxides, we have, let me share this with you. Now we have the P5O10, NO2, SO2, SiO. So these are examples of the, just few examples of acidic oxides. We can also call them the acid anhydride. That's when when they react with water. Okay, we also have basic oxides. Basic oxides are actually, remember, acidic oxides are non-metals that dissolve in water to form acidic solutions, or non-metals, some non-metals reacting with acid with oxygen. Now we also have basic oxides. These are metallic oxides. Now they are basic in nature, while they react with acids to form salt and water. Remember, acidic oxides react with base to form salt and water. That's a neutralization reaction, right? And basic oxides,
Yeah.
they are basic in nature. That means they are metallic oxides that react with acids to form salt and water. An example of these bases are potassium oxide, which is K2O, magnesium oxide, which is MgO, calcium oxide, which is CaO, and lithium oxide, which is L2O. So, but I hope you know that soluble basic oxides, please write this down, that soluble basic oxides are called alkali. Soluble basic oxide, that's basic oxides are soluble in water, they are called alkali, either alkali or alkali, as some may call it. Now, we also have the amphoteric oxides. Now, when you talk about amphoteric, meaning that they behave like both acid and they also behave like base. So that means they can react with both acid and base. They can react with acid and base. An example of this type is called, we have them, the ZnO, zinc oxide, the aluminium oxide, and the lead oxide. These are examples of amphoteric oxide. Remember, they can behave like acid and they can behave like base. Okay. We also have neutral oxide. While amphoteric oxide, they behave like both acid and base, neutral oxides, they are neither acidic nor basic. So they are not acidic and they are not basic in character. And that's why they are neutral. An example of such is, for neutral oxides, example of such is water, CO, and N2O. Remember, CO is a neutral oxide, while CO2 is an acidic oxide. Do you understand that? CO is a neutral oxide,
Yes, sir.
CO2 is an acidic oxide. Okay, and let's just talk about peroxide. Now, these are higher oxides. That means they give hydrogen peroxide when reacted with a dilute acid. Now, we also have peroxide. Example of this peroxide, we have them as barium peroxide, calcium peroxide, we have sodium peroxide, and we have hydrogen peroxide. Now, I'll just give an example of peroxides. Okay, these are examples of peroxides: barium peroxide, calcium peroxide, sodium peroxide, hydrogen peroxide, the most common one that we see. Okay. Wow. Let's look at uses of oxygen. Now I've been the one talking. I need you to tell me now. Give me different uses of oxygen.
So rekindle glowing skin.
Sorry?
To rekindle glowing skins.
Sorry, I didn't hear that.
To rekindle a glowing skin.
It's using what?
Rekindling glowing splints.
Okay. Rekindle glowing splint. That's a test of oxygen.
For respiration.
Yes, for respiration by plants and animals. Okay. What else?
um,
Okay, I'm waiting.
Welding.
Sorry?
Oxygen is used in welding.
Sorry, I didn't get that.
It is used in welding.
Okay, it is used in welding when it mixes with oxy acetylene flame using welding, cutting of steel. That's an exothermic reaction. Okay. Okay. Okay, what else again?
Mm,
Are you still there?
for this as life supports for diving.
You said?
As life supports for divers.
As life support. Okay, good. Okay, now it is used in oxyacetylene flame for welding and cutting of steel. Is used in respiration by plants and animals. Use it as breathing aids in hospitals. Okay, and liquefied oxygen is used in explosive and as rocket fuel. All right. So I think the last thing we should be talking about, or the next thing we should be talking about, is the next thing we should be talking about is the ozone layer or ozone shield. We know definitely that the ozone layer is a region of the Earth's stratosphere that absorb most of the sun's UV radiation, ultraviolet radiation. Now, it contains high concentration of ozone, and the ozone layer, is mainly found in the lower portion. We know that the ozone layer is found in the lower portion of the stratosphere. All right. Um, what are the ozone gases? Now, the depletion or reduction in levels of the ozone has caused most times these worldwide changes in climate and increased warming of the atmosphere due to some gases. Now, the greenhouse gases, now we know them as carbon dioxide, and this, because of this, has released what we call the greenhouse effect. Now, greenhouse gases, we know them as carbon dioxide, the water vapor, and the chlorofluorocarbons, that's the CFCs. These ones, they absorb the radiation at certain wavelengths, that's the radiation from the sun. And because of that, they form a blanket. Thus, they trap all the outgoing heat, such as glasses or plastic do. Now, when they trap it, I was using this for example for somebody today. I said, um, look at this um, bottle. When when sun, it's just as if the earth is like this, the sun shines, illuminates in this bottle. Now, the greenhouse gases, now normally when it's radiating this bottle, the gases are meant to go out. The radiation is meant to go out. But what happens is that the greenhouse gases, what they do is they trap they trap the sun, they trap all the radiation and make sure that it doesn't go. Rather, it comes back to us, thereby affecting us. Now, the gases, they form a blanket, trapping all the outgoing heat, and this leads to rising sea levels and most times atmospheric warming, most times the melting of ice, which has led to desertification and flooding. So this is actually what it has happened. Okay. Um, Next one we're meant to go into is halogens, but I would definitely ask you some questions. I would definitely ask you some questions. Okay, let's go to our trivia time. All right, so look at this question. Number one, okay, I hope you're looking at the questions very well. I hope the questions are not scaring you. Okay, in which group is oxygen in the periodic table? Hello?
Group 6.
Sorry?
Group 6.
Group 6, okay. Which of the following is an allotrope of oxygen?
Ozone.
Sorry? Don't tell me you're looking at your notes. Come on, close the note though.
Ozone.
Ozone. Don't look at your note again, oh. Okay. Number 3, oxygen is prepared by heating what?
KClO3.
Eh? No, don't look at that note. I want to see your I want to see your eyes looking at the screen. At the screen. Don't look down. Okay, number 3 is what?
B.
Sorry?
B.
B, yeah, KClO3. Potassium trichloride. 5. Now, number 4 is what?
Allotropy.
Okay, number 5.
Reacts with both acids and alkalis.
Correct. Now, those were objective questions. I think I should have objective questions for hydrogen. I was just teaching and teaching without any objective questions. Okay, now let's go into objective questions for hydrogen. Okay, let's see this objective question. Okay, if the valency of hydrogen is 1 and that of oxygen is 2, the formula is what?
H2O.
H2O. One of the isotopes of hydrogen is
Deuterium.
number 3. Hydrogen is prepared in the lab by the action of dilute H2SO4 on the following metals, except
Hmm.
except
Zinc.
what?
Zinc.
Eh? Come on, look here. Don't look down.
Um,
I'm not hearing you. What are you saying?
Aluminium.
Okay, now, have you heard of the reactivity series?
Yes.
Okay, so Which of them is lower than hydrogen in the reactivity series?
Sodium.
Sorry?
Sodium.
Sodium. No, sodium is higher. Actually, it's iron.
Mm.
Sodium is actually higher than one of the principles is if I am higher than you cannot react with me easily like that. I should, I would only respect those that come, just like now maybe, but in some families, if the senior person or the first child, the eldest child is, maybe they have meat to give to all of them or gifts to give to all of them, what happened? The first child takes his own first, then this followed by the second, followed by the third. In fact, the last child is always unlucky because before every other person has taken, yours is just the smallest. So that's actually what's happening. Sodium can react with oxygen, zinc can react, aluminum can also react slightly. Then iron may not react with hydrogen, sorry. Now, number four. Number four is what?
Hydrogen.
Sorry?
Hydrogen.
Hydrogen, correct. Can you write the equation?
Uh,
Are you done?
no.
What happened? Are you having issues with it? Okay, awesome. Sorry, did I remove that? That was okay. On a large scale, hydrogen is produced from what? Yep. Hello.
Yes, sir.
Yeah, you didn't answer the last question.